Hi, I'm Adan Vela. I'm coming from the Department of Industrial Engineering and Management Science. A lot of my work involves modeling human decision making and how can we leverage those models in order to optimize system performance. Where's this? All right. So I want to start by sort of giving everyone an idea of my prior work, and probably what I'm best known for is my research in air transportation management. And so I've done a lot of quantitative modeling and optimization, simulation, and sort of the standard problems that we see in air transportation. So there's everything from capacity estimation, demand delay modeling, traffic flow management problems, both at the airport, en route, and terminal area environments. Probably what I'm best known for within this is path planning, conflict detection and resolution, and collision avoidance. I'm actually very proud to say that I've worked on ACAS-X, which is the next generation collision avoidance system that is going to be put onto all future aircraft, which is really exciting. So anything air transportation related, I'm quite strong at. But within that, I sort of have a unique take on it from other folks in the field. So I actually come from a controls background in robotics, and somehow that transitioned into optimization and air transportation and an interest in human factors. And specifically, what I'm interested in is the role of the human in decision making and how we can sort of tie ideas from control theory into air transportation research and more broadly, human interaction with robotic or intelligent or some sort of decision support system. So sort of in line with this, I think we can think about the span of decision making and where control theory and human in the loop control has sort of been prevalent. One of the first uses of modeling the human as part of a control problem had to do with this pilot-induced oscillation. So basically what ended up happening is there's a dynamic of the aircraft that is out of phase with the human control input. And so the end result of this is that you'd have a lot of early fighter jets crash when pilots tried to land. And the solution to this was, hey, let's model how humans respond to their visual input and respond to the system in order to sort of remove that pilot-induced oscillation. So much of my work sort of takes this idea but abstracts it up to higher levels of decision making, specifically the tactical, operational, and strategic. So how do we understand the role of human decision making in these processes? And this is especially true when we look at problems like traffic flow management. All right. So let's sort of understand why there's a challenging problem. So any good decision support tool that we're looking at in the future, especially that's AI-based and sufficiently complex, what's going to end up happening is we're going to have human operators working with these systems, wondering, what is it doing? Why is it doing it? What is it going to do next? And this just sort of increases the computational workload on this user. And so really my research, again, taking from this control systems perspective that we have to understand the plant and the controller, is to sort of flip this paradigm around where we start having our AI system or our decision support tool be asking those questions about the user. Specifically, what is the user doing? Why did the user do that? What is the user going to do next? And the general hypothesis is if we end up having a good model of human decision making, then this decision support tool becomes an actual team member. And so really, most of what my work looks at is how do we model the human decision making as part of some stochastic process. So what I'm going to do very quickly in the next few slides is sort of provide an overview of some of the research projects that we have ongoing in our lab. Some of these are funded. Some of them are sort of through startup or through fellowships. So the first one we are actually doing with Professor Keithley and Kowalski and another faculty member at Georgia Tech. We sort of asked the question about how can workers self-optimize or manage their interactions with a multifunction robot? So a lot of times we talk about human to robot teaming, where that robot is a single function robot, right? But now we're sort of asking the question, what if this robot can do 10 functions, right, intelligently, but they vary in ability of each of those skills? Can the human worker self-optimize or manage that relationship? More interesting for us is we're starting to look at the role of the supervisor, right? So how does the supervisor sort of guide the worker-robot partnership? This is especially interesting because one of the roles of a supervisor or manager is to do things like assess, evaluate, train, hire, fire workers, right? But now we have a robot worker. And so one of the fundamental questions is, can a supervisor accurately assess the work contributions between a human worker and a robot worker, right? And then how do we provide feedback? So that's a super interesting project. I'm continuing my work in air traffic management. Of course, this is expanding to unmanned aerial air management or advanced AAM, which is sort of the eVTOL air taxis type stuff. This is coming into play in a few different ways. So one of our interesting projects that we have going on right now is we're actually we're developing or working towards an AI model of an air traffic controller. And the idea is if we can build this model, then we can imagine deploying it either at untowered airports, or we can use this model of an expert air traffic controller to help train new air traffic controllers, or we can use it as a safety check, right? So we can look at the decisions of a human air traffic controller and compare it to this AI system and then assess some sort of safety margin. Another project that we're sort of working on, again, in this sort of AAM, eVTOL field for autonomous aircraft is rapid assessment of landing site suitability. This is actually a DoD project through an STTR, which is quite interesting. So we're looking at, how do we do path planning and identify emergency landing sites when we're doing logistical operations for the DoD. Another project that is crossing our fingers, it looks like we're going to get funded if the money gets pumped out this year. We're looking at how AI systems can work with minimally trained pilots. So what we're trying to do is look at psychometric measures to assess the cognitive state of, let's say, a medic on an autonomous helicopter. And when things go wrong, who do we trust more, the medic or the AI system? Especially given the fact that the AI system might have broken sensors, or the stress of the medic might create poor decision-making, right, or poor responses if there's some sort of interaction between these two entities. In line with this idea of modeling human decision-making in cognitive states, we sort of extended my work. I've sort of extended my work into education analytics. So again, I'm sort of looking at how do students select their classes, their enrollment patterns, and their decisions, and how does this affect their academic outcomes? And so, again, most of my work that I think is unique from other folks is most other researchers tend to take a static image of a student, like these are the classes they took, these are the grades, we're going to predict something. What we're really interested in is how do we understand trajectories, right? So trajectories tend to be more meaningful than just a static snapshot of a student. And so we've had some really interesting results related to optimal enrollment strategies, identifying prerequisites, even like ordering of classes or spacing between classes. We recently had this finding that was sort of counterintuitive, where we showed a decrease in academic performance of a student could actually increase retention and graduation rates, which was highly unexpected. But we are able to do this when we focused on the academic trajectories. The last project that I sort of want to talk about is a big DHS project that we've received funding for, where we're looking at the evolution of individuals and communities through their engagement patterns and language usage. And so what we're doing is we're studying social media data to understand radicalization trajectories, hidden networks, and can we find hidden radicals, right? So somebody presents themselves in one context when they're really another. Can we identify that through their language usage? So basically code switching, if we want to think about it in terms of social science terms. With that, one of the things that I want to encourage everybody to do is we run a regular seminar with DHS researchers, folks from DOJ, and other researchers to present their work. And the idea is we want to get social scientists and quantitative folks together in order to solve problems related to DHS. So with that, I'll sort of end by saying, who do I like collaborating with? So up top are social scientists who work in, education, human factors, psych, cog sci. I love that sort of stuff. Future collaborations, I'm really interested in folks who do computational fluid dynamics, so urban winds. So if you want to think about UAVs flying around cities, folks who do work in communication networks. So what is the communication network structure we need for our next generation air transportation system? How do we design antennas for these aircraft? And then I'm especially interested in working with folks who have some involvement with database systems, distributed computing, enterprise architecture, which we don't really have as a field. And so those are sort of the big ones. And of course, any industry partners or anybody who's interested in doing air transportation research. Always love to talk to you. So that's it. Thank you all.